We are group 4, and today we're going to be talking about reasoning mathematically. Today I will be discussing inductive reasoning and its differences from deductive reasoning, as well as how we use it in our everyday lives. You may be surprised at how many mathematic techniques we use daily. My name is Alyssa, and I will be giving you a deeper look at inductive reasoning and its uses. So what is inductive reasoning? Inductive reasoning is a mathematical strategy we use to draw a general conclusion based on information obtained from specific examples. The conclusion is drawn is classified as a generalization, and the generalization can be proven wrong with one or multiple counterexamples. So basically what that means is your answer is your generalization, and it can always be proven wrong in deductive reasoning with just one or multiple counterexamples. At the bottom, you'll see this is the path to inductive reasoning. An observation is made, a pattern is discovered, a hypothesis is formed, and a theory is formulated. Your theory can always be proven wrong. Okay. Inductive reasoning versus deductive reasoning. With inductive reasoning, we start with specifics and end with a generalization, whereas with deductive reasoning, we start with a generalization and move on to specifics. So those kind of counterbalance each other. In inductive reasoning, it's used in mathematics for problems such as finding a population trend for years to come, or like at the bottom, I have an example of number patterns and patterns of blocks and their movement. With deductive reasoning, it's used in mathematics to deduce information to form a true statement, such as if quadrilaterals have 4 sides, then a square is a quadrilateral. Both of those statements are true because quadrilaterals have 4 sides and a square has 4 sides. There's no counterexample to that. It cannot be proven false. How do we use inductive reasoning in everyday life? At the bottom, you'll see a guy sitting in traffic, and it says, I should be able to leave my house at 8 and make it to my chosen destination at 8:15 because I've done it the past 2 times. You're taking 2 specific times, and you're coming up with the generalization that you'll be able to make it again at 8:15. What you don't count on is traffic or flat tire or anything like that, so you could be proven wrong. On the right, you'll see a house, and it says, all of the houses on Pine Street are falling apart. I live on Pine Street, so my house is falling apart. You could come to that generalization, but then realize with the counterexample that your house is not falling apart. There's nothing wrong with it, even though you live on Pine Street. Inductive reasoning has multiple uses, from finding a time of arrival to predicting the population for our state in the year 2025. Depending on the specifics given, any generalization can be made. After viewing my part of this presentation, I hope you all have a deeper understanding of inductive reasoning and see that you may use it in your everyday life without even noticing. Now, Ms. Heather is going to discuss reasoning mathematically.
So today I hope to show you a few different ways you can use representations when trying to solve mathematical problems and reasoning mathematically. Everyone has a different way of learning, and to me, I think representations are beneficial when it comes to mathematics. My name is Heather, and I hope you learn something more about mathematical reasoning by using representational reasoning. Mathematical reasoning is the critical skill that enables a student to make use of all other mathematical skills. Even though there are several that you can use, I'm really going to focus more on representations. In mathematics, a representation is an object that captures the essential information needed for understanding and communicating mathematical properties and relationships. If you look to the right and you see the bar graph, it's just one type of representation that you can actually use. On the opposite side is another representation. You can use bar graphs, pie charts, line graphs, or pictures. Again, as a visual learner, pictures kind of help me answer questions a lot easier by dividing them like they did in this picture with the apples. You take the red apples and the green apples and you add them together, you get 5. These other graphs are used in everyday life as well. You see them when it's talking about populations. You can take a city and use a line graph, and you have several cities at once to see whose population is higher or which one's declining or factors of why they're declining. Graphs help to understand the data that you're getting a lot easier than just looking at words and trying to read them. If you look at this problem on the screen, it takes pictures. The squares and the circles, if you go to the next diagram, you'll have 7 squares and 3 circles, which will all add up to 10. To me, it's easier to take objects and add them together than it is to look at it and know what's going on. With there being several ways of mathematical reasoning to go by, inductive, deductive, and also representational, for me, representational works easier because I am a visual learner. And now Chelsea's going to go over more inductive reasoning along with deductive reasoning.
A rule of math is, if it seems easy, you're not doing it right. But in all seriousness, this is so true. Until you fully understand the math that you are doing, it might seem difficult for you. What is inductive reasoning and how we use it every day? Inductive reasoning is a problem-solving skill that we actually use every day. When we use inductive reasoning, we will start by looking at the problem closely, form our conclusion, and make a prediction. We can look at any problem or scenario and notice if there is a trend or pattern, and that is what we will base our prediction on. A great example of how we do this every day is every quiz we have had in the past has been very easy. Therefore, our test is going to be easy as well. And here is just another example of inductive reasoning. If you look here, the first equation, notice how the number line grows. You add 1, then you add 2. The pattern here is add 1, add 2, add 1, add 2. And if you look at the second equation, it goes from 1 to 4, which is adding 3. Then the next number will be 2, which is subtracting 2 from your previous number 4. So there is a pattern in this equation as well. You're going to be adding 3 and then subtracting 2. And this is also another example of inductive reasoning. I'm going to get a pointer here. Okay, if you look at your first square, you'll notice that the circle is in the top left corner. And then looking at the second square, notice the circle is in the top center of the square. If you look at the third, the circle is in the right top corner. The fourth square, it is on the right center. And on the fifth square, it is going to be in the bottom right-hand corner. If you notice that pattern, it's moving in a clockwise motion around the square. So you're going corner, center, and so on. So with this, in finding the pattern, you can conclude that the next circle will be on the bottom of the box in the center. So the answer would be B. And then we're going to look at deductive reasoning as well. It is also one of the keys to problem solving. With deductive reasoning, you will start out with a set of possibilities and you will work your way down to the one accurate answer. It's similar to stating a hypothesis and then concluding. An example of deductive reasoning is if A equals B and B equals C, then A must also be equal to C. So in this equation, the letter A is going to be the same as the letter B, and the letter B is also the same as the letter C. So therefore, A and C, must be the same. I hope now that you have a better understanding of what inductive reasoning is and how to use it. Next, Ms. Keisha will be talking to you about mathematical statements.
Hi, everyone. Thank you so much, Ms. Chelsea. We have a tough topic to talk about, one that I'm not very good at still, and that is going to be mathematical statements. So a statement is just a declarative sentence that is either true or false. And that goes for 4, even in English. So you can declare that 2 times 5 is 10. And that's true, and it's also declarative. So it works for a mathematical statement. the sky is green. That may not be false, but it's still a declarative sentence, so it works. Now, if I were to say, I always tell lies, that's not really going to work for a statement because the sentence, it can't be either true or false, because if it's true, it's also false, and so it's not very definitive. The part where it gets a little tricky is with conditional statements. They're symbolized by if-then statements, kind of like you see in science with experiments and all the fun stuff. So we use P for hypothesis and Q for conclusion. And then they're usually categorized by and or. So if P and Q are either true or false, then P and Q are going to be true or false. But it's also said that if P or Q are true, then P or Q are false. But P or Q both must be false in order for P or Q to be false. I know that's a lot of words and numbers, and it's hard to keep track. So that's how we come across with truth tables. And they kind of give a way for us to have representation for description. So you can kind of see if P is true and Q is true, then P can imply Q, so it's always true. Now, if P is true, but Q is false, then you can't imply Q from P, so that's false. Now, if P is false, but Q is true, it doesn't work as well because you can't imply Q from P because it's already false. And if both are false, that's true. You're going to assume if P is always false, Q is always false. And hopefully that made it a little bit easier to understand mathematical statements. Thank you so much for tuning in.